Hi everyone, welcome back to another Pre-Calculus 12 lesson. We are starting chapter 3 today, which is on polynomials. And as usual, I have split up the longer sections into two. So we're doing the first half of 3.1 today, and we'll do the second half in another video. Again, you have the freedom and flexibility to choose if you want to do both videos together. That's up to you, but I'm going to split them up just so that they're a little more manageable and it's not so much content all at once. So, chapter 3 on polynomials, we'll start with review as usual, but if we take a look at this equation that I am putting a star beside at the top here, you will notice that I've tried to color code everything so it's easier for you to understand and to follow along. But everything that's in red is the coefficient. And to remind you, coefficient is just the number that precedes the variable. So it's right in front of the variable. And the blue notation at the bottom is just to indicate which one is the first coefficient. This would be the next coefficient, and on and on. And the black is just our variable, which is x in this case. And notice the degree, or the blue thing written at the top here. We always start with the highest degree. We write this in descending order, as I have written down right here. Polynomials are always written in descending order of exponents. So that means we would start here with the highest degree, and then the next one, if you look here, so assuming the first one, let's say, was x to the power of 7, the next one would be x to the power of 6, the next to the power of 5, and on and on. So that's all that this is indicating. The n is the first one, the next one then would be n minus 1, the next one would be n minus 2, on and on till you get to x squared, the next one, and then there's no x, which we could write as x to the 0, but that's just the number 1, and it's sort of redundant to write that. We don't need to put it there, so we'll get rid of it. But this is basically the general form of writing any polynomial with any number of terms. And you will see this come up, so I thought it would be helpful for us to just briefly take a look at it. Okay, notice this last one here is called a constant. A constant is just exactly what it sounds like. It stays constant or doesn't change, and it doesn't change because there's no variable to plug in different numbers into so that we could change it. So constant stays as it is, so it would just be a whole number. Okay, so let's do a little bit of review from before, where we take a look at this chart and let's fill it in. These notes you should already have. Again, it's in your class notebook in Microsoft Teams. If you look for your own folder, in there's a section that says class notes. So all of these notes you have available to you ahead of time. You're welcome to print them off, and then you could use them to follow along, or you can have them on a tablet following along, whatever you like, whatever works for you, but find a system that does work for you. Or you're welcome to write them all down as I'm going through them as well. So, taking a look at this, the degree would be this first exponent. We just talked about this in the definition. So the degree here is going to be 4. The lead coefficient is going to be this one right here, which also happens to be a 4. And then the name of this, well, to name it, we look at the degree. And since this is a 4th degree, we would name this a quartic polynomial. Moving on to the next one, the degree would be this number here, so that's a 3. The lead coefficient is going to be this one here, which is a -3, so yes, you do keep the negative sign with it. And when we go to name this, we look again at the degree or the exponent that's on there, and since it's a 3, we would call this a cubic polynomial. So I do believe some of this is review from before, but you might have forgotten or maybe you didn't do it. So good to brush up, and that's what we're doing here. The degree of this next one is right there. It is a 2. Our lead coefficient, again, these are already written for us in descending order. So make sure that you do pay attention to that, because if they're not, then it's your job to rewrite them or rearrange them in descending order, and that's when we get the info for what we're looking for to fill in the chart. Lead coefficient, we can see from that is 5. And this one, if it has a degree of 2, well, this is something that's actually quite familiar to you that I'm going to use often as an example because it is familiar to you. And that is a degree of 2 we call a quadratic. The reason I'm saying it's familiar to you is when we sketch this out, it looks like a U shape. It's called a parabola, and I know that you did this for months and months last year. So I will often use that as an example because I think that it is helpful to refer back to familiar things when I teach you a new concept. So parabolas are going to be my go-to examples because you kind of already know them. Moving on to the next one, when we look for the degree, well, notice the x doesn't say anything, but it actually would be a little 1 that's up there. So I would say this is a degree of 1. And when I go for my lead coefficient, it would be this 3. And then the name of this, again, just like the parabola or the quadratic, notice how it says 3x minus 1. That's like mx plus b. So this is our linear equation showing up again that we've actually been doing since grade 9. So hopefully you're super familiar with that. Just a quick review, built-in review, is that the 3 would be your slope and the minus 1 is your y-intercept. So if I asked you to, you would quickly know how to sketch this out, which will come in handy as we move on to examples throughout the year. On to the last one. It is asking us for the degree. Okay, so I never want you to write this, but just so that you clearly get what's happening here, I could have an x to the 0 there, so my degree would be 0, because the degree always goes with the polynomial. So that's where that comes from. Of course, we never want to write this. It would be ridiculous. So we can leave that off, but it's good for you to know that. And then the lead coefficient, okay, well technically, well maybe I shouldn't have just gotten rid of that because that would help. If we looked at it this way, the lead coefficient would be 4. And that's really all that there is here. So the coefficient is a constant. That's what happens when our whole equation is a constant. And I've given away the name of it. We call this whole thing a constant. Okay, so nice way to start things off. It's kind of nice to know what you're talking about. I'm never going to get you to give me a definition of something, but in the questions, you'll have these vocabulary terms built into the questions and you need to know what they are. So it's good to sort of brush up on this. Notice this part in red here. Note the exponent must be a whole number, no fractions or negatives, and the coefficient must be a real number. I'm thinking you need a refresher on that, so we'll build that in as we go through here. A real number is basically, way back you did a box that had rational numbers and irrational numbers. We called it the real number system, and then it had whole numbers, integers, natural numbers, all that stuff. So all of those together are called real numbers. An example of an imaginary number or something that's not a real number, don't write this down, but just so that you see, is something like the square root of -4. We can't take the square root of that, so that would not count as a real number. But most of the numbers we work with are real numbers. So let's get to some examples. We want to figure out for these next few examples if this is a polynomial or not. We can just go through and write yes or no. So starting with the first one, I'm trying to see, does it fit all these red rules? So there is a square root there, but the square root is on the number. So the coefficient is a real number, so that it does follow that rule, it's fine. And x squared plus 3, that's fine. So we would say, yes, this is a polynomial. Now, if this square root was over the x, then it would not be a polynomial, because if I were to convert that to out of radical form, it would be x to the power of 1/2, and we can't have a fraction. So just to sort of talk our way through this, that's what we're working with here. Looking at example B, we have 2x to the power of -3. Well, a negative sign clearly is not allowed here. So I can say no. Because my variable has a negative exponent, that's a no right off the bat. C is a little bit tricky. There's more stuff going on. I'm going to mention this because you did it last year. We're going to do a full chapter on it this year, but this together is called a rational equation. So we have a polynomial at the top and at the bottom of a complex fraction here. There's a lot of stuff going on. So does this count as a polynomial? Well, if I wanted to get rid of this x squared and write it up here, it would be x to the -2. So according to my rules, no, this doesn't make the cut. This is not a polynomial. So I've purposely chosen examples that will show you what doesn't count, because I think that there sometimes is some confusion surrounding that. Moving on to part D, notice how the root 3 and the x are under the root sign. So I would just want to show you this below. Another way I could write that is 3x all to the power of 1/2. And we know from before I could distribute that half to both of these. So that ends up giving me root x, or x to the power of 1/2, which doesn't make the cut. So no, this is not a polynomial because of the fact that I have a variable under the root sign. Okay, lots of talking, lots of definitions. I'm going through quickly, but I hope that it's familiar because you've done it before. And if not, you can pause and rewind or do what you need to go back to that. Now these little boxes here, I have tried so hard, I cannot get rid of them. So just ignore them if you can. Like, I don't even understand how. I'm trying to delete and it just won't let me. So anyways, please ignore these two boxes here and let's get into these examples. It says the shape of a polynomial graph. A polynomial is always going to be a continuous smooth curve. So there's no breaks in between and there shouldn't be any sharp points or sharp edges on it. So if we're figuring out if this is a polynomial or not, the first one, notice that it is a smooth continuous curve that goes all the way through. It looks sort of like a W shape, which is common for polynomials. So yes, this is a polynomial. This next one, it says no breaks. Well, there's a break right here. So because there's a break right there, this is not a polynomial. And notice how this one has a point right here. So it comes to a point. So this also is not a polynomial. So there's just the definition so that you are clear and familiar with what to look for. If you have a parabola like a U shape or an upside down parabola or a W shape or anything that's like a smooth continuous sort of thing, that counts as a polynomial, but any of these things do not. Sorry, by any of these things I mean the second two. Okay, next we're going to get into specifics here. We could have a polynomial with an odd degree. What do I mean by odd degree? Well, let's take a look. So, if I have an odd degree, that would be like f of x equals x, because although we don't write it, it's x to the 1, or x to the 3, or x to the 5. It can keep going, but you'll notice that the pattern of behavior is going to be the same. When we are looking at this stuff, we are interested in the patterns of behavior. Not so much just on the nitpicky little details, but step back and think big picture and look for patterns that they have in common. Good thing to look for in life too. But anyways, taking a look at these polynomials f of x equals x to the n. So in this case, n would be an odd number versus f of x equals negative x to the n. So I'm going to compare and contrast these. This negative stuff I'm doing in blue below, and the x to the n, the other stuff I'm doing in green, so that we can compare and contrast and get a sense of what these look like. I'm going to really roughly sketch out what these graphs look like, which you probably kind of already know, but if we have just f of x equals x, that would be a line that just goes diagonally through. So basically this is saying y equals x, so it makes sense that that's what our line looks like. But let's compare that with f of x equals negative x. And the nice or interesting thing about this is this ties in perfectly with with the last chapter on transformations, because notice that this negative sign in front of this x would be a reflection over the x-axis or the y-axis. It's actually not going to make a difference in this case, but any which way that we look at it, remember those leading questions I asked you? Does this negative affect my x values or my y values? Well, this is an unusual situation where the answer would be both because of how it looks and how it's set up. So I could take it and flip it across the y-axis, and that's what it ends up looking like. Okay, so now when we move on to x cubed, this would start down here, and it would sort of make this type of shape. And before I do the blue stuff, I want to show you the pattern of behavior. So we're going to do x to the 5 as well, which ends up being similar to x cubed, but it would just reach the values because the exponent has gotten larger. It just means that it would reach the y values much quicker and the y values at the bottom and the negatives much quicker. So it would end up being like a narrower version of what I just sketched out. So it would be kind of like this. So it's the same idea as the stretches that we did with parabolas. If you, just to put things into perspective, so this x to the 5 is really stretching things out to reach the higher y values much sooner. So at smaller x values, we would reach higher y values. So I hope that that helps to put things into perspective for you. So I want you to think of the pattern of behavior that you notice, meaning I want you to look for similarities between these three green graphs. So let's start off with this one first, and then we notice the next one and this one. So basically we're looking to see, like, what do they all have in common? And hopefully you're able to recognize or see they all start down here. Oh, let's maybe go through and label our quadrants. This would be quadrant 3. Notice how they all start pointing downwards in quadrant 3. I am going to call this end behavior. That is what it's called. I know you can barely even read that. I'm sorry, I tried my best. It's hard to write on this thing, especially when it's standing upright like this. So hopefully you can make sense of that and write it neater yourselves. End behavior means that the green graphs, they start down in quadrant 3. And they end up in, notice this is quadrant 1, this is quadrant 1, this is quadrant 1, quadrant 1. So the reason that we go through this stuff is, like, math is all about patterns. What we're ultimately doing is we're looking at all these different scenarios or situations, and we're looking for the pattern. So it's only when we step back and look at the big picture that we're able to point out or recognize those patterns. If you're just zoomed in, this is true of life too. If you're just zoomed in on this one situation or one graph, and you just go about doing that without paying attention to the other stuff around you, you wouldn't be able to pick up on this pattern. So we really are trying to use this theme in this course to start to pick out patterns and look at the behavior of what's going on. So let's finish off with these blue ones. If I have my x cubed in green, then negative x cubed, well, notice that that's going to affect my y values because the x cubed isn't in brackets. I mean, because it's cubed, it's not actually going to make a difference, but it's going to affect all of the y values. So we can take this and flip it over the x-axis. So what ends up happening is I get the same type of graph flipped around that way. And the same thing's going to happen with the negative x5, except a much narrower version because of the fact that it's being stretched up to higher and lower y values at a much quicker pace, or much earlier x values will achieve those y values. So let's look at the end behavior of that thing. So end behavior would be that it starts up in quadrant 2. So this is quadrant 2 to refresh your memory. And that's happening, look, here and here and here. So again, we're drawing our attention to the patterns of behavior when we switch to big picture thinking, comparing all of these. And we could have gone on to x to the 7, x to the 9, x to the whatever. Anytime it has an odd degree, you're going to see the same type of behavior. This would end down in, well, it's down here, which is quadrant 4. And you notice it here, and you notice it here in quadrant 4. And remember, we use Roman numerals to represent the quadrants, which is maybe kind of nice because with all the different numbers, variables, things going on, that makes it super clear that we're referring to the quadrant or the coordinate plane. Okay, so we're going to do the same thing but with even degree polynomials. So let's maybe start to look at the same type of thing. We are still looking at patterns of behavior, but maybe we're just going to do 2 of them. We could extend this to go x to the 6, x to the 8, on and on and on, but we're going to end up seeing the same types of things happening. So let's just do it this way for now. You already know this. X squared, we know from before, is a basic parabola. X to the 4, let me also say this. I could have a bunch of other stuff here happening, like plus 2x minus 1, da 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 da, which might change this, or would for sure change this, to have different patterns, like it might end up making a W shape and put in all sorts of other things, but we are looking at the most basic stripped down form of what this looks like, which would be just like a parabola, but a narrower version for the same reason as before with the cubic graph that I just showed you and the quintic graph that I showed you. So it's the same type of behavior that you see happening. So maybe when we look at end behavior for the green stuff, we can say it starts up in quadrant 2 and it ends up in quadrant 1. That's going to be true for x to the 6, x to the 8, on and on and on. It is true that there could be other things happening in between like this, but notice the end behavior would still be the same. So don't worry about if there's other stuff following this x to the 4. Right now we're stripping it down to just the basic form, which is what I'm going to continue to do throughout this whole course because I think that's the best way for you to learn, is to strip it down to the basics. We'll start with that first, and then we'll slowly build on more complex things to that once you've got a handle on the basics. We'll look at the basics in order to pick up on the patterns, and then we start to complicate things a little further after that point. Okay, looking at this negative, we already know it's going to flip it upside down and go like that, and we already know this is going to flip it upside down and go like that. So this would start down in quadrant 3, and it would end down in quadrant 4. So let's sort of compare and contrast to the last scenario. Notice that with the odd degree polynomials, they start and end in different directions. And with even degree polynomials, they start and end in the same direction. They have to, if you think of the pattern of behavior that the graph would show. So when in doubt, go back to something that you know for sure, and that's parabolas. Parabolas always start and end facing in the same direction, even if it's been reflected and flipped upside down. So do pay attention to that and use that to help you to figure out what's going on. Another thing I just want to throw in here that you probably already know, but I think it's a helpful reminder. We read a graph the way that you would read a piece of paper, like a newspaper or a page or a textbook. We start from left and read it to the right. It's a good habit to get into, just to go from smallest to largest, or to get into, I feel like a lot of math is just clarity and organization. So if we get into that habit of viewing it that way, it helps to simplify and to bring some clarity to what we're working with. So hopefully that's helpful. Okay, so this we've kind of talked about. End behavior is what we call all that stuff we were just talking about. So end behavior of f of x equals x to the 4, so that's the stripped down version in its most basic form, compared to a not so stripped down version in a not so basic form where we do have other things going on. The key here is that we would have the same end behavior, and it's determined by the leading term in the polynomial, meaning the fact that it's an x to the 4 is what helps us to determine that. Okay, so it's nice to just have that written, but it's the stuff that we were talking about while looking at the graphs. And then take a look at this green box, just as a refresher. When we way back learned how to name polynomials, a monomial is when there's only one term. So x to the 4 is an example. A binomial is where there's two terms, and remember that terms are separated with a plus and a minus sign. And a trinomial is 3 terms separated with plus signs. So a constant value in a polynomial. Okay, this is good to know. The constant value is where it crosses the y-axis. I've highlighted them in yellow here. To show you, let's change this to yellow, to show you what's going on here. So notice that the plus 6 in the equation is also the place where it crosses the y-axis. So the minus 3 in the equation is also the place where it's going to cross the y-axis. So to give you a sense of what we're doing here is I am basically pointing out patterns of behavior for graphing out polynomials. So things to look for are significant aspects of the graph, because there's going to be a lot of things going on with really long equations, and it can be tedious and painful. But if we are able to look through it all and get to the stuff that matters and pick that out, oh, this too is also symbolic of life. There's so much stuff, especially in 2020, so many things coming at you. Discernment is what you call it. Discernment is such an important skill. It's taking all this stuff that's coming at you and picking out what actually matters. So what actually matters, well, one of many things, is that this constant value at the end is the y-intercept, or where it's going to cross your graph. So if we know the end behavior and we know the y-intercept, or that constant value, then that's already giving us a pretty good general sense of how to quickly take an equation and just like that be able to sketch out what the graph's going to look like. Okay, so that's what I wanted to point out and what I wanted you to get from this. And then it says in this next one, find the y-intercept. So notice in equation A, well, I guess I can just show you this. Find the y-intercept. Look at equation A. It says f of x equals negative 2x plus 1 cubed. So I know that this looks different than this last equation that I just finished showing you, where you were quickly able to just pick out the y-intercept. But in this, it's a little more complicated. It's not in that same simplified form as it was up there. So I just want to use some previous knowledge that you know, and that's like, maybe I'm going to look back at the graph, but what do we know about the y-intercept? What we know is that it's the point where it crosses the y-axis. So that also means that that's the point where x is always equal to 0. Always, that's going to be the case. For it to be a y-intercept, x has to be equal to 0. So I can use that information in my equation to quickly be able to pick out what the intercept is, even though it's not in this expanded form like the previous examples. So when I take a look at this, I notice that this just becomes 1 cubed, so actually it's just -2. So my y-intercept would be at the point 0, -2, and maybe I'm being really nitpicky and particular with this, but I want you to get into the habit of writing it as an ordered pair, because I feel like that's, again, this is about clarity, and that makes it super clear what it is that you're referring to and where to find this on your coordinate plane. So write it as a point. 0 because it's the y-intercept, and -2 is what we just found. Looking at part B, same idea. If we're looking for the y-intercept, we know that that means plug in 0 for x. You don't have to write out every single little step, but I just want to make sure that it's super clear for you in your notes, so I am writing out every single step. But ultimately, you want to plug in that 0. It's 0. So the nice thing about that is you can probably just do this in your head by looking at it. But when we take a look at this, we're just doing -2. That's going to be wiped out. So -2 times 1 and just times 4. So it's -8. And again, I just really like to make it super clear. Good habits to get ourselves into. And that is that our point for our y-intercept would be at 0, -8. So just tying it into what we just looked at in the graphs above, like that, the equation, this isn't a bunch of separate stuff you're doing. I mean, these are separate examples. They're not the same equations. But you are, whether you're graphing something or looking at the algebra and the equation, those are just both different ways of looking at the same thing. Some people learn visually, some people learn through the algebra and doing the equation. Know that it's all the same thing, and those are different tools that you've picked up on over the years to help you to really get a big picture perspective and understanding of what's going on. So I have picked out the questions that will go nicely with what we've focused on in this video, and that's page 119, numbers 1 to 3 all. 6 to 8, remember that this just means odd letters, so you're going to do A, C, E, etc. So you do the first one, then you skip. And again, this is my suggestion to you. It's totally up to you. If you feel like you're a little iffy on these and you could use some more practice, then do them all. So get into the habit of you deciding, you getting to know yourself and deciding what you need. So that's it, and that was so good. So I'll see you in the next video shortly.